Hey guys, so today we're going to be talking about chapter 4.5, proving triangles congruent. Okay, we're going to be looking at angle, side, angle, and angle, angle, side today. So with angle, side, angle, okay, so ASA, anytime you have two angles and the included side of a triangle that are congruent, and then two angles and an included side of another triangle, both triangles will be congruent. Okay, so what that looks like, we have angle A is congruent to angle D. Okay, we can tell by the two arcs. Side AB right here is congruent to DE, and angle B is congruent to angle E. Okay, so again, angle A is congruent to D, B is congruent to E, and then this side right here, AB, is congruent to DE. Okay, since we have angle, side, angle, or two angles and the included side, then both our triangles ABC and DEF are in fact congruent. Okay, so moving on to a proof. Actually, before we do a proof, another way that you could see angle, side, angle, if we have intersecting triangles like this. Okay, so they're touching at a point, and we're told we have these congruent angles, and we have these sides that are congruent. Okay, last thing, if there is an X shape right here on our triangles, remember these are known as vertical angles, so the purple is vertical angles. Okay, and those are always congruent. So we have two congruent angles, purple and blue, and the included side, which we colored with pink. Therefore, both of these triangles would be congruent. Now, moving on to the proof. All right, so we need to use ASA, angle, side, angle, to prove that these triangles here are congruent. So I'm going to look at the information they give me. They tell me that QS bisects, so QS here, bisects angle PQR. Okay, PQR is this blue angle right here. All right, remember bisect means to cut in half. Okay, so QS is going to cut PQR into half. Right? And then additionally, PSQ is congruent to RSQ, so that's these two angles right here. We need to prove that triangle PQS, so PQS, is congruent to RQS. Well, look at the information that's given to us, okay? First, we want to start with our givens. So our first statement will be QS bisects PQR, as well as these congruent angles, congruent to RSQ. Okay, the reasons for these statements is they're given to us. Okay, given. So now I'm going to take my given information and my picture and kind of dissect it a little bit, figure out what's going on. So I'm told QS bisects this angle. All right, remember bisect means to cut in half. So I know that since this angle is cut in half, each half is equal to itself. Okay, so I can say angle PQS, that's this angle right here, is congruent to angle RQS, so this one over here, and the reason for that is they're being bisected. So definition of bisect, okay? When an angle is bisected, it's cut in half, right down the middle. Okay, next thing I want to look at, I have QS. So this segment right here, QS. So if I was to take apart these triangles, PSQ and RSQ, we'll notice that they both have SQ, right? Which is right here, QS. Okay, this is a shared side. Since they have a shared side and it's in the same corresponding position, this is congruent. Okay, so for my third statement, QS is congruent to QS because of the reflexive property. All right, if a mirror was to sit on top of that line, could be the same line. Okay, so this line here is reflexive, right? So last thing we have is number 4, and that is what we're trying to prove. Do we have enough information? Okay, so PQS is congruent to RQS, and how do I know that? Well, I have my purple angles, I have this QS side that's included, and then I have congruent angles here. So, angle, side, angle. Angle, side, angle. Okay, moving forward. So our next theorem we want to talk about is angle, angle, side. So with angle, angle, side, we are going to be looking at two angles and the non-included side. Okay, that's the important word here, non-included. All right? So when you have two angles and a non-included side, two triangles are congruent. Okay, so if angle A is equal to angle D, angle B is equal to angle E, and this non-included side, right here, of BC and FE, or EF, are marked congruent, then we have congruent triangles. Okay, so moving on to our proof. Okay, so we are given that angle DAC, so this right here, is congruent to BEC. Remember, if you're not sure of the direction, just trace from the letters. DAC, angle in the middle, BEC, angle in the middle. Okay, those are congruent per my givens. And then also, line DC is congruent to line BC. Okay, so I need to prove that these two triangles are congruent. Right? Well, I have congruent angle and a congruent side. For this example, we're trying to use AAS, so I need another angle to prove that. Okay, so if I'm looking at my triangles with them overlapping, it might be a little difficult to see. So let's make a drawing of them separated. Okay, so we have A, C, D, and then we also have E, B, C. Okay, so we were told A and E are congruent, and then B, C, and DC are congruent. Okay, so when we take these apart, we have the congruent parts marked. Last thing I know, in this initial picture, our triangles are overlapping. Okay, so we only have one C angle here. When we take them apart, we notice each one has a C. Okay, this is because these are corresponding angles. All right. These angles, since they overlap, they are congruent to each other. So I can say that I have two angles that are congruent and a non-included side. So writing that out, we say, given angle DAC is congruent to BEC, side DC is congruent to BC, and also, remember this purple C angle, C is congruent to C by the reflexive property, because remember they share that angle on both triangles. Okay, we can say that triangles ACD and ECB are congruent by angle, angle, side, because we have two angles and a non-included side. All right, and on to our last example. Okay, so real-world example, we have Jeremiah's working on a community service group, building a bridge across a creek. Okay, the bridge is going to span the creek between the points B and C. Jeremiah finds a fixed point, D, to use as the reference point, so his segments are going to have the same relationships. Right, A right here is the midpoint of CD, and DE is 15 feet. How long does the bridge need to be? So, what we do in this picture, okay, so I'm going to label some things. DE I know is 15 feet. A right here is the midpoint, okay. I can tell I have two right angles, so those are going to be congruent, right? Remember, A being a midpoint means that DC is going to be cut in half, okay? Midpoint is a key vocabulary word. Cuts in half, okay? Midpoint is kind of like bisect. Midpoint shows that middle point. So, if I know that A is my midpoint, then DC is cut into two equal parts. So I can mark that as being congruent. So DC, I'll do a different color. So DA will be congruent to AC, okay? Because remember, A is a midpoint. So we have two congruent angles and a congruent side. Last thing we need, one more angle or a side to determine this congruence triangle-wise. All right? So, if we're looking at this relationship here, and I can make the picture a little bit bigger, draw it out for you guys. So if we have A here, we know these are right angles, and then these sides are congruent. Remember when we talked about vertical angles, okay? When you have this X shape in your lines, the angles that sit in the corners are vertical angles. These angles are congruent, okay? So having these congruent angles here right at our midpoint area, this gives us an angle-side-angle relationship. Okay, and what do we know about angle-side-angle? Our triangles are congruent. So if we know our triangles are congruent, look at our corresponding sides. Okay, so we have DE. Okay, DE is going to be congruent to BC. And remember, we're trying to solve for BC as our bridge. So if DE is congruent to BC, we'll know that BC, our bridge, has to be 15 feet as well.